So, um, basically, this is my presentation of kinematics of dye bleaching. This is by Jacob, me, and Bert. Um, yeah, so basically, the goal of this project was to see how each dye would react differently with bleach. And to find this out, we were gonna measure the order of each dye, the reaction order, and we were going to essentially use that to compare against the order of bleach. So now, why do we need to do this? In many mainstream food, snacks, candies, food dyes are used to make food or candies more appealing. They add color, they differentiate flavor, and whatnot. The two food dyes that we used were Blue 2 and Red 40. And why is this important? So this is important because almost 14 million tons of clothes are thrown out each year only by Americans. And what our goal is that maybe if we learn how to bleach things better, we can increase the longevity of clothing when removing stains. So, for example, if you didn't really need to bleach something for super long, we could recommend how long to bleach it for and minimize damage to the textiles. And so essentially what we're claiming here is that we believe that each dye tested will have a unique reaction with bleach, and we can identify which color stains will be harder to remove. And we're going to use orders to find that. And so some of the evidence we have down here is, so basically to test the absorbance or to essentially find what order each dye is. So for Blue 2 and Red 40, we did like an absorbance test over 180 seconds. So we mixed 1 milliliter bleach with 1 milliliter of red dye. We mixed them in a cubit and then put them in the UV vis spectrometer, and then we connected that to my laptop. And we kind of recorded what the absorbance was over 180 seconds. And then to test the absorbance of the blue food dye, we did the exact same thing as mentioned before, so we did it with both two dyes, and yeah, to measure that. And then we were able to graph the concentration and the natural log of concentration and the 1/over concentration. And when we were given the absorbance through the spectrometer, we essentially were able to calculate the concentration using Beer's law. And we did the calculations in Excel. Previously, I linked all of our Excel sheet in our notebook. So if you want to see that, you can go back and see that. And then essentially to find the absorbance of the bleach, this was the hard part. We did 3 different dilutions, so 1:1, 1 milliliter dye, 1 milliliter bleach, 1.5 milliliter dye, and 1.5 milliliter bleach and 1 milliliter dye. And then we did 2 milliliters of bleach and 1 milliliter of dye. So essentially we kept the dye, the standard, and then we changed the bleach to try and find the order of the bleach. And we essentially collected the change in the concentration was found using Beer's law. So once again, as I mentioned before, for the dyes, we used the Beer's law to find the concentration of bleach. And we used delta R over delta T, and then using the 3 rates ratio. So the ratio of the 3 rates, we were able to determine the order of bleach essentially, which was one or first order. Yeah, so essentially right here, what we have is we have 4 graphs, and this graph shows a linear line, and this is going to be for the blue dye. So we did use 2 different graphs. One of them for the blue, we used 1/over concentration, and for red, we used natural log of concentration versus time. And this was mainly just because it was more apparent to us using these 2 graphs, but it doesn't matter because essentially it ended up working. It works out because each order is going to have one of them is going to be one of these three graphs is going to have a straight line, and two other are going to be curved, and there's a pattern. And we did link the like a good summary that would show it how all the different orders. But essentially, this one right here, we used a straight line for the 1 over blue, concentration of blue. And that one had a smaller r squared value. So the higher the r squared valued, or the closer to 1, the r squared valued, the better the regression equation is. So it's going to work out better, and it's going to be a better line of best fit. So clearly the linear line doesn't work for this one. But then down here, or it doesn't work as well, I should say. But then down here, what we have is we have the a polynomial regression equation, and the r squared here is going to be much higher. You can see it better when you zoom in, essentially. So it's like 0.991 versus 0.959 right here. So what we can assume is that for blue dye right here, blue versus time, what you're going to want to have for 1 over blue concentration versus time, you're going to want to use a polynomial equation. And what that's going to mean is that's going to mean that blue dye is a first order equation, according to the Purdue linked thing that we had, and also what we've learned in class. So we linked all that information to make it much easier. And then right here, what we have again is we have a linear line. Now, however, the regression equation here, the r squared, is not as, doesn't fit the data as well as the polynomial line. So this one right here, it's a natural log of red is the polynomial graph. So we can assume that right here, this is going to be a second order form. So essentially for blue dye, it's going to be first order, and red dye is going to be second order. So then what this tells us is that we're able to conclude that blue follows a first order rate, and red is going to follow the second order rate, just like I said before. And we, like earlier I said, we calculated that bleach was a first order. So essentially what this tells us is that because blue dye follows a first order and bleach follows a first order, they are going to they're going to be like they're going to work together kind of, and they're going to be able to react at the same rate essentially, and that's going to mean that it's going to react faster, the blue dye is going to bleach faster, and it's going to end up being better. Right here we have our r squared values. This kind of essentially goes through. I'll just read it real quick. We can identify that which order each dye is based on. The r squared value in the trend line of blue 2. The linear r squared is 9.59 versus the polynomial r squared of 9.99 or 991. So essentially what that says is that the polynomial is better for the blue equation. And then furthermore, the red, the r squared value for linear is going to be much less than the r squared for polynomial. So this does follow a second order, because this is a different formula. This is going to be the 1 over absorption versus the natural log of absorption. And then some limitations that we encountered along the way were the inability to record the exact peak absorbance. So we would essentially measure, like we'd mix them and then we would put it in the spectrometer, and that caused a lot of problems because while it's being mixed, we're losing that absorbance values that we would love to have. So maybe if we could mix it in the spectrometer, I know that was in the quiz said we're not supposed to do that because it's bad, it could mix it, whatever. We don't want to do that. So, but that would have helped a lot. Maybe it mixes it in it, something like that would have, maybe a little better of a spectrometer, who knows, So to rectify this, it would have been able to nice to record it, the absorbance, basically the second of, with some fancy spectrometer technology, something like that. So a future direction we'd like to take this is, we'd like to, a future direction we'd like to take this experiment is, instead of using the wavelength of each dye, using the spectrometer to differentiate the wavelength in respect to ranges. So essentially looking at the absorbances we're reading at slightly different wavelengths could be beneficial visually when trying to depict results. This would also help with errors such as smudges or whatever in the cuvette. That would be really helpful to help us out. Essentially, in conclusion, they're going to kind of like bleach at the same time. However, the red, because it is a second order, is going to bleach much faster because it's going to, the concentration of red doubles and it will bleach 4 times as fast because it's kind of like 2 or whatever the concentration to the second power, right? So it's gonna bleach a lot faster. This will allow us to conclude that blue 2 will bleach slower, than the red 40. And this is confirms our initial claim that each dye will have a different reaction with bleach. So yeah, essentially we can confirm it, and we have some references down here. Not too much. I mean, most of the references were stuff that we learned in class, but our 14 million textiles thrown out in the US was from this reference. So that's essentially it, and I hope you learned something. Maybe not. I mean, you probably knew what the answer was. Sorry I wasn't able to make it to class, but we're here, so thank you.